Thank you, Professor Reddy, for giving me this opportunity. As he has already told, I know Professor Reddy since 2000, and I also thank all the participants who have joined for this webinar. So my topic is on valorization of industrial byproducts and mine tailings. I belong to the institute, which was originally known as Indian School of Mines. This institute is started in 1926 by the then Viceroy, Mr. Irwin. So this institute has a history on this mining and mineral technology. And coming to this institute is in Dhanbad, also known as coal capital of India. People might have heard about it. Then coming to this byproduct, I had this experience of knowing about industrial byproducts in 1991 when I went start my MTech program. One fine morning, my professor said that I have got 2 buckets of material called fly ash. You have to characterize it and tell me what are those materials. So that is how I came into contact with an industrial waste called fly ash, that is from the thermal power plant. Over the years also, I have contacted with many stalwarts in the geoenvironmental engineering. I should thank Professor Reddy, I am in contact with him since long, and I have learned many things from his experience and research. So now, as I understand this valorization, byproduct, and geoenvironmental engineering, I'll try to present. I need your comments for further improving my knowledge in this regard. In my title also, I have not written anything called waste. I have said it as a byproduct. Because my philosophy is that ignorance make it a waste and knowledge convert it to wealth. When it is ore, minerals, or we say product, because we know all about it, all about the process, that's why we are saying that these are resources. About some of the products, we have got partial information, or the process, we say it is byproduct. But if we have got very limited, we can say it as a waste. So this is my understanding that how people define it as sometimes byproduct or waste. What's the need? As per this OECD Global Material Resource Outlook, they have made a review till 2011 to know about the demand of different materials for survival of this earth, humanity. So if you look at this, all this requirement is in gigaton. So I'm sorry, I have not written it, the unit. But this requirement, if you'll see, the maximum requirement is sand, gravel, and the cross rock. That is 27.5 gigaton. Whereas if I project, if it is projected 2060, it is almost double. So this is the requirement of sand, gravel, and cross rock. What we say it as geomaterial. And this is then very high percentage in compared to other material. If you say coal, metal, even the metal you say 19 gigaton, but whereas sand and gravel we need 54.8 gigaton. Where we'll get this? So we have got only one resources we call lithosphere, or this solid sphere, that is earth. So it has got some natural sand, gravel, and rock. So this can be say as the surface sand deposit, river sand deposit, or terrestrial hard rock, which we cross it to make it a sand. So mostly this river sand mining is very common because it does not need skilled manpower. It is freely available without doing any pre-processing. So this is the most widely used material as far as to manage the requirement of this geomaterial. But now with the demand, and this has got many problems, particularly in terms of aquatic life, failure of the river beds, and even it has gone up to social impact in terms of law and order situation. So many of the states in India also, they are going to stop the river sand mining. The alternate source is surface sand deposit like Evelyn deposit. One example I can say it. Or third option is go with hard rock crossing, which is also mostly now being followed in many parts of India. Whereas if we look at the other side, we are producing a good amount of industrial waste or byproducts. So if you can process it, this can also substantiate and make it an alternate construction material. And if that's after getting it into the construction, after a few years, then this can be made into construction debris and processed to come as again construction aggregate. So this is what the way we have to recycle. And here my catch is that this one is this hard rock crossing, one of the alternative to get the demand of these natural resources. So this is some statistics in terms of Indian context. And in terms of, you will see that not only India, other developing countries also, when they want to give the house or habitation for their inhabitants, demand for this is still going to increase. In terms of sustainable development goal, it's my talk will concern on this number 9 and number 12. So that is 9 is industry, innovation and infrastructure. And this 12 is responsible consumption and production. So here in the picture, I have shown some of the industrial waste in and around my place. So most of the time industrial wastes are considered as a problem due to its toxic metals and ions. But again, if we'll see these toxic metals or heavy metals, if I'll say it, are also considered as the resources or critical minerals in terms of mineral engineering. So now the ideal process should be to extract these metals by the metallurgist or with help of other multidisciplinary experts to make our product suitable for construction, and again we can recycle it to so that we can return back. If we cannot do anything, we can return back to the mother earth the material which is no more toxic. This we can say as a safe and wise principle. So I am starting with coal and coal combustion residue. So in India, though in other countries, they are no more using this coal as the source of energy. But in India, so far we are also using 71% as coal, which is the main source of energy. When we are extracting so much of coal by the side, to extract it, we are generating also coal as overburden or coal mine overburden, which is mostly sandstone and shale. So the sandstone it came to my mind, can we make it as a resources? Now when this coal burn, it generates the coal combustion residue called as fly ash. Way before in 91, as I said, when I started using or investigating fly ash, the utilization was only 5%. But over the years, if you'll see, the utilization percentage increase, so also generation. So in between this R means this gap, what we call it as a legacy ash. So this is being dumped, which has taken a vast tract of usable land, sometimes hindering the expansion of the energy. So now the emphasis is on, as you see, the gap has reduced to use this legacy ash. Now, if I look at this diagram, most of the fly ash being used in cement industry and roads and flyovers. So this will say that how this gap can be reduced. Now, the government of India has made an audit of all the fly ash companies to show about generation and utilization, and the idea is that very quickly we'll get rid of this legacy ash. So the point lies in how to expand in the variety of way it can be used, so also in percentage of its use. So when I'm coming to the industrial waste in general, I have shown you one chemical composition being a geomaterial. First, we need to know what are the chemical composition. Accordingly, also it is divided as hazardous and non-hazardous waste. My topic will be concentrated on non-hazardous waste. So when if you see the coal mine overburden, this is one of my topics. And other is the fly ash and red mud. So in this, if you'll see, some of the chemicals of these industrial byproducts has very imbalanced percentage of the oxides, for which we are not able to accept as a common geomaterial which we come across as a civil engineer in general or geotechnical engineer in particular. So now, first one, as I say, green, that is your coal mine overburden. All the material looks normal, like what we have seen in the other geomaterial. So here we try to first use it. If I cross this sandstone, I am going to get alternate sand. What are the criteria I should consider? First criteria to be used as a construction material is called deleterious or innocuous. So this is through, otherwise there will be alkali aggregate reaction. To check it, we need to go for this testing. And if you'll see, all the three varieties of coal mine overburden collected from three different layers, if you can say exactly, from same mine. So all these are innocuous, so there is a potential to use it. Next parameter comes when I am going to use it as an alternate sand, is called flowability. So this flowability talk about this workability. So here I have shown if this is my 3 crossed rock from the coal mine overburden, this requires more amount of water in corresponding to the standard sand or the river sand. This is RS is river sand. So that is one of the aspect we have to keep in mind. Water requirement is more. This has also been compared with other industrial waste. Next comes the strength. So as per ASTM standard, all these compressive strength are satisfying, and we can define it as type S or type M mortar. Further investigation requires the durability of the concrete, that we can use it through carbon dioxide ingression or chloride ingression. All these tests has been satisfied when I'm going to use crossed OB as replacement of fine aggregate in cement mortar. So as I said you, the advantage was that all it was green and it was just like alternate material, but still there was a issue for this flowability. Next, I am coming to other waste, that is a fly ash. So if you'll see what I have done, I have shown you the typical chemical analysis, and mostly we defined as our ASTM defined the class F fly ash and class C fly ash based on this aluminum, silica and iron content, or based on the calcium content. But rather than, we can also define further as given by Vasilev and Vasilev in terms of its, this will indicate whether it is acidic or basic. So this will help for better utilization of this fly ash. And then, as I said, along with the coal and coal combustion, I'll use two other, or also in comparison to this, other two industrial waste. One we call it as a bauxite residue with the aluminum industry. There, if I'll plot it, you see it is more towards the iron. So now the efforts by the mineral is to extract iron. This, once the extraction is done, this will further help us to use it as a geomaterial. Till that time, its use is still limited in terms of its civil engineering or in other construction material. Similarly, coming to GGBS, it is almost 100% used material because it has got the properties which can be directly mixed to the cement and concrete. Now, next, when I'm coming to the geotechnical perspective, I define this into two groups. One is based on the sites through mechanogenesis. If I say the Indian river sand is naturally made, and if I say GGBS or ferrochrome slag, they are also, I can say, industrial byproducts, and this crossed one. So this process consists of both thermo and mechanical genesis. These are coarse grained. But coming to the fine grained, we had volcano ash. So that is through thermal and natural genesis. But when coming to the fly ash, where the coal is burnt at 1300 to 1400 degrees centigrade and it generated. So now when I compare this, when I'm talking about volcano ash as a pozzolanic material, so also I'm considering fly ash as a pozzolanic material. So that has tempted to put it in cement and concrete. Now similarly, some of the process we are doing it biogenesis. Now that is your calcium carbonate compound, that is also now where through processes we are able to identify and get it. And third is chemical genesis. So always I have tried to compare it with the natural, what it has clay minerals that has been generated through this natural process. Now I am talking about bauxite residue or red mud. That is also one chemical process, but we are doing it in an industry. So that way, we have to see, when I see this industrial waste, we have to compare in this to find out its valorization. Going further, I have shown you here the shape of the particle. If you see the shape of the particle for the fly ash, it is mostly spherical and depends upon the type also. Here I have written a very specific called floater or cenosphere. If you see, it is so spherical and well, almost of equal size, though it contains 1 micron to 100 micron. And such material has got high valorization in compared to when we have got some heterogeneous material or the fly ash as a whole. So this is being used even in the cosmetic industry. So these spherical particles here as a civil engineering, we used as for rolling effect in cement mortar and for other workability. Whereas these also taking the small smoothness and chemistry, it has been used for cosmetic product. So this another aspect which need for the valorization. So also we need to know its internal structure. If I want to say how much I can add fly ash in a concrete or cement. This was the fly ash when I treated with hydrofluoric acid just to see what is there inside. You see there is an internal arrangement of crystal structure that is mostly mullite. These are in the crystal phase and these are not reactive with the cement. So this much amount will not give you a pozzolanic reaction. So also in this another fly ash particles, surface, smooth surface, whatever the glassy phase was there, those have been used. But these whatever remains are some of the iron compound is also there, which will not react. Another important aspect for valorization is its X-ray diffraction. We need to know the minerals. As I said, we need pozzolanic and that should be glassy phase. So these are the minerals of the fly ash, mullite, hematite, and so on. But we are interested more of the glassy phase. So what we have done based on the literature survey, I try to plot based on the calcium content and the home position. Here I am showing the home position. So this indicates the type of glassy phase. And if you the higher lime content, these are better glassy phase, which is more of like calcium aluminate. And here it is aluminosilicate. So here it could be have some self strength or self-hardening strength, but here it is mostly a pozzolanic strength. So this needs cement. Here you may not add any cement, still it can bind particles. Then what I did, so I collected the information to find out how much glassy phase is there. Because from the X-ray diffraction, we can find it out, but always being civil engineer, we try to find out some small tricks. So based on a ratio, I found this fly ash, this is fly ash I've collected from 1950s till 2000. So that way it is a wide variety of collection from different parts of the world. So depending upon the type of industry, I mean the efficiency of the plant, based on a ratio, that is potassium and aluminum, we can predict the amount of glass content in a fly ash. So this will define the type of glass or the fly ash it is. Accordingly, people will be interested to buy it more. So similarly, another use of this X-ray diffraction is when you get anything as a geometrical 75 micron to 4.75, we say it is a sand. And it tempts us to use it as a fine-grained aggregate in concrete cement. But this size is not sufficient. If I'll go with the minerals, I am taking one minerals here, which we call it as ferrochrome slag. So if you'll see it as, it has got high amount of chromium and also the magnesium oxide. So its size as sand, but the X-ray diffraction says something different. If it is a standard sand, it's quartz, quartz, and quartz. But these contain some other thing. So what it happened, when people tried to use it directly in construction, there was a reaction and many cracks in the structure. So similarly, another waste I collected from the bauxite residue. There also, if you'll see, it comments hematite, magnetite, and all these things. And look at the particle shape in compared to standard sand, and this is from the bauxite residue. And it's very difficult to find out how they are different. Only the color is different. It is red, and this is the sand color is grayish. So we should not deceive by this only size. We need to go for its mineral and the chemical composition. So this is further what I have said you. Sometimes we differentiate, separate it through magnetic separation, thereby taking out some of the chromium and other iron compound, making it dominant in alumina silicate, which we call it as a quartzite or a close towards our natural sand. When we are using for the geomaterial, any coarse grain, whereas this industrial has got different shape and sizes. So for that, we can do the analysis. Nowadays, we are doing image analysis through advanced software like MATLAB, and there we should find out this well-rounded, rounded, and all these things. These are required for its valorization or utilization for different products, like when I am going to use it as a control low strength material. And in that, more important when it comes to, again, I wanted to show that correlate with this flowability. So this shape of the particles are accordingly when I'm talking about spherical, angular, subangular, this will define how that material will behave or its workability will be with different percentage of water content. Here I have again shown with the same material in a different way, just to say the wet flow and dry flow. And this natural sand, it is 0.4 to 0.6 is enough. Whereas for this industrial waste, depending upon the type of industrial waste, it definites differently. So you have to be aware about this. So when we are going to use it, so there may be bleeding, and then that needs flowability. So we need in this range, normal flowability, and the bleeding should be less than 5%. If we can do that, we can achieve this, then as I've shown you here, we have got very good values in terms of UCS and CVR, which can be used for the pavements. Further, to know its compactness, we can use the same type of equipment we use for the concrete, because when I'm using this industrial waste, so there are always a chance the void space may be more. So sometimes we need to, when we have compacted and used it for pavement and other things, we may go for this type of ultrasonic pulse velocity to measure its compactness. When it comes to its high value utilization, now people are trying or being tried for since 5-10 years as an alkali activated material, or what we are calling it as a third generation cement or green cement. So I saw this diagram because when I was visiting, I found a literature. So it is written the pyramids are not carved stone, but soft limestone with a high kaolinite content could be the activation of it in those days to prepare stones. So coming to that industrial waste based on the chemical, what I have shown you, many of the industrial waste has the potential to be as one of the precursors at least for this alkali activated material, also called as inorganic polymer or geopolymer. But there I need to characterize it, and here I have shown with 3 samples only. Here you can make it like a mortar cube I have shown. I have also shown like aggregate. So after saying all these things, so now I'm coming to now the keyword what we call as a sustainability, and we are adding further is resiliency. So this is called triple bottom line environment, society, and economy. Further, if I add it to resiliency, so then it become getting a sustainable material now needs to be studied in the framework instead of simply writing like a sustainable material. We need to study these three aspects. So, sorry. So here, as per MIPS 2002 and also colleagues developed a procedure. So we have to, the target, I mean, the challenge is that even if we have got said requirement level, environment, economy, and social, the indicator level, it's a challenge to find out indicator in local or regional basis. And second one, identifying the weights of these indicators that also depend upon the regional or local basis. Then only we'll be able to find out a number to tell my solution is a sustainable solution instead of just using the word sustainable material just after doing the technical investigation. So here I'll show one example. Here one example I have shown here with, as I said, now the challenge with the Indian industry to use those legacies. Here I have made a small comparison. If I directly use the fly ash from the plant or take it from the pond, that is what we are calling it as a legacy ash, how is going to affect the sustainability. So if you look at the diagram, sorry. So in terms of different indicators, fresh fly ash has got better sustainability value in comparison to fly ash from the impoundment. So now the main target should be that we should not allow any more fresh ash to get into the pond. Another example I have considered for this one overburdened sand production unit, virtual sand production unit in and around Dhanbad area. With this process diagram, we did the sustainability analysis on environmental aspects. We compare it with river sand. And if you look at this, river sand has got almost, if you see, equal for all these aspects. Whereas, if I'll go to OB sand, it is less. Now, you just see, in terms of environmental price, if I'll convert to INR, OB sand has got very less impact. And we have to consider here what I said, in comparison to cross sand, this OB sand has also advantage. Here I don't have to go for the blasting, which is done for the cross sand, which needs blasting. Then one more aspect which mostly done by the social scientist here, one of our student, we went with some survey with different stakeholders, taking the inputs first, the questionnaires getting vetted by the experts. If you look at this, academia, local public, production and supply and workers, all their inputs has been considered to find or take the social aspect. And Then we try to find out for different indicators, criteria, and requirement, compare with the river sand, OB sand. Only the assumption in this case that the weightage, because the industry or the policy planners, they need to put this. For academician, we have provided an hypothetical index or the weightage, I will say. So based on this, in all aspects, even if I consider 33 equal weightage for environment, economy, social, or with 60% social aspect, always this OB sand is found to be more sustainable compared to the river sand. Then where is the problem? The problem is this, what is called as technology readiness level. So this technology readiness level now, we have to take care of it. Many a time our academia effort stops in 3 or 4 level. At this point, we need to get support of an industry to come out of this valley of death and to get a business model that is number 9, TRL number 9. So for the fly ash, if you'll see, this is for the fly ash, for pavement construction, cement, concrete, embankment filling, it has become now a business model. But still some of the use, as I said, it is not yet done. Whereas in the bottom ash, now when I'm visiting for different thermal power plants, they are worried for this bottom ash. It is only 12 to 20% or 18%, others say. But this is the product which is remaining unutilized. Most of the fly ash, almost 88%, whatever the fly ash they are generating, they are able to sell it. But this bottom ash is a problem. And if you'll see, many of the things have been stopped at level 4, level 5, level 6, and so on, except as a fill material. So now the efforts are here to use it, or to industry should come forward to use, make this chain complete so that it becomes a business model. Another thing what I came to know from them, from the industry, when they are saying ROI, return of investment. So as an academician, we propose all these things. They are now asking for this return of investment policy. And being academician is becoming difficult, but we can take help of an economist to sort out this problem. So this is for other industrial waste. Similar models are there. The last aspect is policy, this role of standard. I am showing a diagram here, which I did during my MTech thesis. I had 3 types of fly ash. One is navely, high lime content. Other is the punky, which is the fine grained fly ash. But paricha, it was getting very high quartz grade. When I do the compaction at immediately after the, I take the usage immediately after the compaction, these are the values I am getting it. But I keep it outside the desiccator. After 7 days, almost has 0 strength for the paricha, and for punky also reduced substantially. If I put it inside the desiccator, I was getting the strength. So that time it was very difficult to explain, but later on I found this is due to apparent cohesion, which I could explain and publish. So for this reason, immediately people are not accepting use it in embankment and so on. But when Indian Road Congress give a prescription that if you have to cover it with the excavator natural soil or granular cell, then railway also design standard, they propose that if you have got a pond ash, then cover it with earth cover and morum. So then now it is being used as the pavement material. So unless these policy planners make it or accept it, so its utilization in vast quantity is not possible. So with this, so if I come to my conclusion, so there is a demand of this construction material. We need to go with 3R, and our it should be reuse of this industrial waste, what I presented it today. Appropriate characterization is important. We were saying waste to wealth, but now the target should be waste to molecule approach. As I said, many toxic material, what we say toxic or heavy metals, is a resources for many chemists or metallurgists. So we have to analyze up to molecule level to find out whatever it is therein. It can be used or better valorization. To come out or improve the TRL, there is need of an industry. We should compare the sustainability aspect to convince the policy planners. We need the standards. Then only the professional engineers will get the confidence of using it. This heterogeneous nature of overburdens or tailings many times is not shared. There is a data transparency is there. And this valorization is a multidisciplinary expertise. As I was saying, even though we need social scientists. So with this, I acknowledge all my funding agencies, my institute, IIT ISM Dhanbad, and the research scholars and collaborators who has helped me to study all these things and to so that I could present it to you. Thank you very much.
Thanks, Sarat. Very nice presentation. So there are a lot of people attended your webinar, so I'm sure it is very, very useful to them. So I think you made a very strong case for use of